In this lesson, we will discuss mining diverse patterns. We will go over mining multiple level, multidimensional, and quantitative associations. Let's start with breaking down the multiple level frequent patterns formulation. At the top, we have the item milk with a support of 10%, and under that, there are different variations like 2% milk, skim milk, maybe other categories. So now suppose we set up our minimum support to 5%. What will happen? The top level item milk will easily qualify because it supports 10%. But many subcategories like skim milk will fail to reach the same 5% threshold. So here is the key issue. Using the same minimum support across all levels, also called uniform support, means we only capture broad patterns. In other words, detailed patterns at lower levels are ignored because their support are naturally small. To address this problem, we introduce a level-reduced minimum support, like level 1, 5%, level 2, 1%. We don't lose potentially useful patterns at finer levels. For efficiency, a good rule of thumb is start with the lowest minimum support across all levels, then filter using the right threshold for each level. The multiple level relationship often result in redundant rules that need to be filtered. Consider the two rules. Buying milk also implies buying wheat bread, support equal 8%, confidence 70%. Then 2% milk implies wheat bread with support 2% and confidence of 72%. Notice how the second rule is simply a subset of the first one. 2% milk is a subset of milk. Now, suppose that the sales of the 2% milk are about 1/4 of the total milk sales, then the fact that the support drops from 8% to 2% is not surprising at all. However, if the subset rule deviates from what is expected, let's say the support of the 2% milk implies wheat bread is 6%, that is much higher than expected. So such a deviation suggests unusual or surprising behavior which is worth investigation. To summarize, when ancestor and descendant rules have similar confidence and expected support, we keep the more general rule and prune the descendant rule because it adds no new information. However, if the descendant deviates significantly from the ancestor's expected behavior, then we keep both for further analysis. Up to this point, we assumed a single minimum support threshold for all items, which in practice doesn't make much sense. Think about big stores. They sell bread and milk, but they may also sell watches and diamonds. So setting minimum support to 5% will for sure capture bread and milk patterns, but will miss out on these rare patterns like the watches and diamonds. On the other hand, if the minimum support is set too low, then we're going to get those rare patterns, but also many trivial, unuseful patterns. To address this issue, the intuitive solution is to use a customized minimum support, which means assigning different thresholds to different groups. For example, diamond and watches might have the 0.05% threshold, where bread and milk can be at 5%. Now, the natural question is, does this break algorithms like a priori or FP growth? The answer is no. With some adjustments, they still work. The key idea is when evaluating an item set, you compare its support to the minimum threshold of the items inside it. That way, an item set contains a rare item is judged by the rare item's lower threshold. Everything we have seen in association rule mining has been single-dimensional rules. For example, buys X milk implies buys X bread. Here, the only predicate we are looking at is buys. But in real life, we often have multidimensional rules which involve two or more dimensions or predicates. There are two main types: interdimension association rules, multiple predicates, but none are repeated. For example, age X from 18 to 25 and occupation student implies buys Coke. This rule combines demographic information, age and occupation, with purchase behavior. It's called interdimensional because it spans multiple dimensions of data. The other type is hybrid dimension association rules. These can include repeated predicates. For example, age X from 18 to 25 and buys popcorn implies buys Coke. Notice that buys appear on both sides of the rule. That's what makes it hybrid. It mixes attributes like age with repeated transaction behavior. More on attributes. Attributes can be either categorical attributes or quantitative attributes. For these categorical attributes like a profession or product, there is no natural ordering among these values. For interdimension rules, we often use a data cube to explore across categories. For quantitative attributes or numeric values like age or income, these have an implicit ordering and we often need to discretize them or apply clustering, maybe gradient-based approaches to use them effectively in rules. Now, why this matters? Imagine you are analyzing customer transactions, but you also have extra data, like when customers sign up for a credit card. These credit cards actually provide age, address, and more demographic information. So combining these demographics with the purchase data allows to discover richer and multidimensional patterns, like which age groups are likely to buy certain products. Moving on to quantitative associations, which involve numerical attributes like age, salary, or wages. Discretization means breaking numeric values into intervals. However, we need to be careful when we perform static discretization. For example, if we discretize age into fixed intervals like 0 to 10, 10 to 20, 20 to 30, and so on, what happens to age 0 to 10? They probably are not buying anything, so including that range group doesn't make sense. So instead, we can use dynamic discretization, which adapts to the data distribution, which in return allows focusing on meaningful age ranges, let's say from 20 to 40, or wherever the majority of customers fall in the distribution. Another approach is a clustering-based association. Here we first perform one-dimensional clustering on numeric attributes like age or salary, and then find associations. In general, clustering adapt to the data and often produce more meaningful groups than static intervals. Deviation analysis is particularly interesting because it mixes categorical and numerical attributes. The key idea is to compare the behavior of a subgroup against the overall population. For example, gender equals female implies wage mean equals to $7, but the overall mean is $9. Here there is noticeable deviation because the subgroup female earns less than the population average. And this can be valuable because it highlights the differences between subgroups and the overall population. The core idea in mining extraordinary or interesting phenomena is demonstrated in this example. The left-hand side of the rule, we have a subset of the population, and on the right-hand side of the rule, we have an extraordinary behavior observed in that subset. For example, gender equals female implies wage mean equals $7, but the overall mean is $9. This tells us that within this subgroup, the average wage for females is significantly lower than the overall average. However, we still need a form of statistical confirmation, so we only accept this rule if a statistical test like a z-test confirms that the inference with high confidence. Otherwise, the observed difference might just be random noise rather than meaningful pattern. More on mining extraordinary phenomena, we can also explore sub-rules to analyze smaller subgroups. For example, gender equals female and south equals yes, then the mean wage seems to be even lower, 6.3. Or for a quantitative attribute like education in number of years, it implies a certain mean wage. So sub-rules lets us drill down in these subsets of the population and see how patterns can change under different conditions. Finally, rare patterns have very low support but can still be very interesting. For example, somebody buys a Rolex watch once a year or upgrade to a new phone or computer every year. But to capture these patterns, it's often useful to set individualized or a group-based minimum support for different groups of items. In summary, we discussed mining diverse patterns.